Yes, thank you very much for the invitation. Great pleasure to be here to discuss with you. I arrived last December, so it's almost 1 year I've been working in the bureau, and it's quite an exciting adventure for me, coming from Canada. So 2 Canadians tonight, that's nice. So what I'll do today is, in 20 minutes, try to bring you to a journey where weather prediction comes from, where it's going, and probably the best way to do that is to do sort of historical perspective. So, and I'll try to, as I explain the history of numerical weather prediction, give you all the essential elements to achieve a weather prediction. And of course, supercomputing is an important component of it. And so I'll mention a lot, I'll put emphasis on the supercomputing aspect of this. So, first, to do a weather prediction, you need to have observation. In Australia and Canada, this was done in the mid-90s. In Montreal, Charles Smallwood started doing this each 6 hours for a long period of time. McGill University started in Montreal in 1863. That was the observatory. And Clark Ross in Albert and Sir Charles Todd in Adelaide done the same sort of thing in the 19th century. So you have all those information, people measuring the atmosphere, temperature, moisture, etc. But something was missing. If you want to do a prediction, you need to bring all this data to the same place. So in the 19th century, the telegraph was invented, and that was an opportunity to bring data to the same place so you could do a forecast. You could imagine that you are sitting here and you know that someone is sending a telegraph to you, say, on the west side, with prevailing wind from the west, there's a storm coming. And you could imagine that by the distance, the wind, well, I'll get the storm in a few hours now in Melbourne. So that's the idea. If you have this information centralized, you can do a forecast. First one who had this idea was a well-known person in Australia, Robert Fitzroy, who was the captain of the HMS Beagle. Well, he's also the founder of the Met Office in the UK in 1854. So that started the idea that we could predict weather. Predicting weather based just on the tendency that you can see from the storms and the wind is not very efficient to have a correct prediction. And the first people who figured out that to do a perfect prediction of weather would be to solve the Navier-Stokes equation over a planet in rotation. And the first one to have this idea was the American Abbé and the Norwegian Burnet. So these equations are complicated. I don't want to put too much emphasis on that today, but they are well known to be nonlinear, unsolvable by analytical techniques, and essentially those two people try to do prediction with them, find a special solution, but they were not able to go anywhere. So that's not the story there. It was a first step forward. You have telecommunication, observation, and you have a theory to make the forecast. First one to really think about that was Richardson, the British. He said, well, those equations are very complex to solve by hand, but we could discretize them in discrete point, let's say 100 kilometers from one other point. So we could do the calculation that those equations are telling us to do, given if we know what's the wind, what's the temperature, how this will evolve in time. Of course, we start looking at a different type of algorithm, calculation techniques to do that. And at the beginning of this conference today, the additional room of people with computers, they used to call them computers. Well, Richardson had the same idea. We need to use computers, people making those calculations. So he thought about this big spherical room with gallery of people with the map of the world, as you see, Africa, North America. And those people would do calculation, and you would have exchange of communication between different points with the people in the middle there. So he talked about this in 1922, a little monograph, well, almost disappeared. It was found by accident. And in that monograph, he looked at, to make a reasonable forecast, let's say for Europe, he realized that it would need 50,000 people. And well, he stopped there, and he said, I'll do something else in my life. So that was, beforehand, a massively parallel supercomputer with no one telling him this will happen one day. So we had to wait for the first supercomputer. And of course, in Australia, Pearcey was developing a very powerful supercomputer, and there was one also in the US called ENIAC in 1950. And von Neumann, which was one of the pioneers of modern supercomputers, decided to do, well, they all knew the problem of Richardson. They knew that we could predict weather, which would be quite incredible and very useful. So he paired with the American meteorologist Jules Charney, and made the first numerical weather prediction based on the ENIAC. I've read also, before coming here, that Trevor Pearcey also, they've done some weather type of calculation also on this machine. I'm not aware of the detail, but I'm certainly interested to see that if someone have any insight on this in this room. That was the first forecast. There's also an interesting story about that. But Charney thinking was also very fundamental in weather and climate prediction. First, he was the first person to realize that this science is so complex and will need so much collaboration internationally that we need to order that type of collaboration. So he wrote this global atmospheric research program in '69, asking all the countries to start working together to solve this problem. He felt this was the number one problem to solve before trying to tackle the climate change or the climate problem. And he said, first, we need to make sure those models predict well weather, and then we'll think about the climate. And he said, we'll do the weather problem in 10 years, it will be solved, and then we'll do the climate one. Of course, we're still working on the weather prediction model. It took more time than he was expecting. Still, he didn't wait for that. And in '79, he proposed another program of research on carbon dioxide in climate. So it was very visionary, and all based on using supercomputers. The '60s. Well, if you ask yourself why a Canadian from Montreal is talking about numerical weather prediction, it's because essentially it's fault here. André Robert is someone who done a PhD at McGill University. He was the first one, because at the time all the prediction and the model were regional. They were not global. But to do a weather prediction more than a few days or to do a climate simulation, you need to have a global model. There was issues with the mathematics of those equations. They have a singularity at the pole, and you need to deal with that. So André Robert's thesis was about that. And just to show you in terms of innovation, technology, one PhD thesis made of Montreal, a place where there's a lot of numerical prediction. The Canadian Meteorological Center is 500 people, and there's 1,000 people in this region who use those products to do more specialized application. So it's a nice example of one thesis can develop a lot of impact. Of course, André Robert had to work with international partners, and Bill Book, which is in the room here today, was one of the pioneers also in numerical weather prediction. A lot of his ideas was used by André Robert to do this first global prediction, which is the ancestor of global model for weather and climate application. So what else was happening at the same time? Well, in the '60s, we started to observe the planet Earth from space. Satellite-based observation was crucial because we had to have a global coverage of information around the Earth to make a prediction. So where we are now, this is essentially what's happening at the Bureau. Bureau is a very nice success story like it was in Montreal. The Bureau is one of the premier weather prediction centers in the world. And I'll say a few words of that later. What you do essentially, we have a monitoring, like I said, the science, like I've shown you at the beginning, and you need to develop those science to put it in operation and provide service. Essentially what you have now, it's an incredible observation of the atmosphere, of the ocean, land surface, solid earth. We do more than weather prediction, we do now weather, ocean, sea ice prediction. We include everything, earth system prediction. At different type of wave, microwave, infrared, etc. All this is put together and processed by supercomputer and resolving the equation of Abbé and Burnet, and to do different application. And now, as you can imagine, this is used to disasters by providing warnings, health, air quality, industry, the renewable is using this information, water, climate, of course, weather, prediction. Ecosystem, we do bushfires prediction with those systems now, which are coupled and are quite exact and very good in predicting where the fires will go. In general, agriculture application, and of course biodiversity. All this is now being sort of application linked to weather prediction and I would say Earth system prediction. Now, that slide is interesting because it tells you how well we're able to do progress along the last few decades in improving the scale of those predictions. This graph comes from a paper I wrote with two colleagues, Boa and Top, and it appeared in Nature. Nature asked essentially us, we don't hear a lot about you in numerical prediction, and we'd like you to explain where we're going, what's the story. So we wrote this paper, and when it was published, essentially said to us, oh, by the way, you'll do the cover of Nature on this article. And that's probably the first time numerical prediction was so highlighted in that sort of journals. Anyhow, there is a graph in this paper that shows that, let's say, this is a forecast at 3 days. Higher it is, better quality it is in your prediction. From 1981 to 2013. And what you see here is a steady increasing in time of the scale. And that's here the 7-day forecast in green, less skillful than a 3-day, of course, but as much good than a 3-day, let's say, we'll take this example, 3-day with compared, let's say, with the 5-day. Essentially, you can show that each decade of supercomputing, better model, push the lead time by 1 day. You increase the scale by 1 day each decade since the 60s. So that's why we call it the quiet revolution of numerical prediction, because it's slow. 1 day per decade, it's almost boring. But it has happened, it has a lot of impact. So why are able to improve that scale? Well, essentially, you can connect that directly to Moore's law. Okay, smart people, of course, more observation. But the fact that the supercomputing power in a log graphic has been increasing linearly like that all the years, was able to use more powerful computer like Cray, Fujitsu, IBM at the European Center in this case. And you can see, if you fix your budget and you push right, you're able to follow Moore's law with the supercomputing system. Then you see the accuracy of a prediction of a tropical cyclone increasing slowly until you start seeing the eyes, the spiral band, which is very important to predict the intensity of such phenomena. So that's where we are now. Of course, a big challenge we have in our science is that Moore's law, we know, is getting slow, saturating, and how we will deal with it. Can we continue to improve things like that for the next 10 years? That's something we'll have to see, but that's the next challenge in our science. Okay, I've been talking about a lot of things, but I never shown you a prediction. Well, that's one. Okay, there's one, and the other one is observation, and that's a quiz. Which one is the observation, and which one is the prediction? The model is at 15-kilometer resolution. It's a global model at the European Center, and the other one is Meteosat observation of the cloud cover. So anyone who's courageous enough to guess?
Observation on the right.
Observation on the right? No. It was too beautiful to be observation. It's too beautiful to be the truth. Okay, so that's where we are now. Here at the Bureau, I saw 3 days ago last week, I saw a presentation from Charmaine Franklin. We can take those big models at 15 kilometers, and we can downscale them to 1.5 kilometers, so 10 times higher resolution. And that's a storm in September 16 from the South Australia, and that's a radar showing the precipitation. And when it's red, it's high rate of precipitation. So that's a radar. You can get that on your intelligent phone. At 1.5 kilometers, that's what you can get from the prediction. At 400 meter, sub-kilometer, it's getting even better. That's the sort of thing we can do. On that one, Charmin made a zoom where there was a report of a tornado, okay? And the tornado is in the simulation. You see it there? That's the tornado. So frankly, last week, the first time I saw a simulation of a tornado in a such large-scale simulation. So that's where we're getting with this. It's getting very, very precise. And 100 meter is sort of resolution we want also for models over the cities of Australia eventually. It will be a reality maybe in 5-10 years from now. So we provide also information at long time scale. So we do it to sub-seasonal, a few weeks, 2 decades now. And that's a product you can find on the website of the Bureau. And the usefulness of those products is incredible. I was talking with a commander from Defense, Australian Defense, not long time ago, and they like to have a seasonal forecast. They have submarine, they want to put them in the shadow, okay, in the ocean. They want to have a seasonal forecast, and to the next few days where the shadow, how it's evolving, so they need to exit their submarine or not. So we provide now seamless prediction from seasons to a few hours. And that's where we are now. The way forward, I'll conclude with this. As a director, I've been for many years the one who tried to understand how I balance my computer resource. This is my blue triangle here. I can increase the resolution, the pixel, but if I do that, I can just do a short forecast. If I want to do a long climate simulation, I need to have a low resolution coarse model, okay? So I'm constrained with that. In my work as director and with the leaders is try to see where in the next 5-10 years I need to invest more to get a good utilization of all this computing resource we'll have. So the future program that I'm developing now with my colleagues, and that will be official in a few weeks from now, is the first priority will be customized impact-based forecast and warning when and where it comes. More localized and timely information from cities and region. That will be nice for the autonomous cars I've just shown, which can gather information. When we'll get 100 meter type of resolution, it will be quite interesting to use in real time. Next one will be, we are in the Southern Hemisphere. Australia, there's not too much observation in the Southern Hemisphere. We rely a lot on satellite. We should do better with that, and we'll put some focus in the future and using better satellite observation, especially that they are freely available due to the World Meteorological Organization agreement. And the next thing we want to invest is a fully integrated atmosphere, ocean, sea ice hydrology model for Australia that will do everything at the same time. Presently, it's all disparate, all separated. We will have a service for Antarctica. Australia has an icebreaker coming, and we want to predict ice, so we take optimal route. That will be part of the service based on that system that will be fully integrated. And the last one, seamless weather and climate insight. People want information from decades to weeks to understand better what's coming. So as a summary, if you want to know more, I've contributed to 2 publications. The one I've already mentioned here, Quiet Revolution and Numerical Prediction. And also there's a book freely available in 3 languages at WMO, the World Meteorological Organization, English, French, and Spanish. And in 25 chapters, we cover all the challenge that's coming in the future on this science. On this, I'll be around afterward, and I'll be a pleasure to discuss with you at that moment.